Our next lecture is on dimensionality reduction. Let's have a look at why do we need dimensionality reduction to begin with. Generally, when we have a problem, we start collecting data for it. But this data is rarely in a unidimensional or two-dimensional form. It always has multi-dimensions or it has a lot of features. What we end up with is a huge amount of data which has many dimensions, and we have collected it at an unprecedented speed, which means that it is difficult for us to not only store all of it but process all of it, simply because of the speed with which we are collecting it. More and more and more is coming, and a huge amount of it is coming. Okay? We have discussed these things in the beginning lectures as well, that data nowadays comes at a lot of speed, it has a lot of volume, and it has a lot of speed. So data preprocessing is important. In order to find what you're looking for, you may need to sift through that data, find some features, use only some features, discard some of the other ones. And in this regard, dimensionality reduction is an effective approach to downsizing data. Majority of the ML techniques that we know of are not very effective for high dimensional data. For example, we can consider a neural network or a KNN approach, and we see that higher the dimensions of data, the more difficult it becomes for us to store or process that data. And this is known as the curse of dimensionality. Okay? Higher dimensions do not result in effective solutions. So we need to reduce the dimensions. Accuracy and efficiency degrades because of that. And then there is another thing where the intrinsic dimension may be small. Okay? We've discussed the concept of good features and bad features in our class, and it's the similar idea that the amount of features that you require to extract some information may be lesser than the amount that you are provided with. So you need to sort through those, what are useful ones and what are not so useful ones. Dimensionality reduction would also be important for problems such as visualizations. We cannot look at anything higher than 2-dimension or 3-dimension. So we need a dimensionality reduction in order to view things. Then data compression, large amount of features, storing of large amount of features require more and more space. Noise removal, some of the features are not good enough, so only they add to the problem more than the solution. Let us look at an example. The problem that we need to solve using machine learning or pattern recognition algorithms is that of document classification. You get the documents from web pages, you get the documents from email. So there are typically different types of documents that you receive. You get from ACM portal, IEEE, PubMed. So all of these have their own formats, their own lengths, their own technical terms that they use inside the document. And then you end up with these terms and some documents. Okay? So you've created some form of a dictionary for every document that you have. It is a collection of presence of some words and absence of some words, and then we count the frequencies. Okay? And based on those frequencies, we classify these documents into sports documents, travel documents, or job documents. The challenge is, or the problem is, that there are thousands and thousands and thousands of terms. All of these resources are different from one another. They come from different types of real-world documents, so they use different languages. Since they have different terms, it is very difficult to use them unprocessed. So what we do is we convert them into some format that can be used for documents from all of these types, and then we process them. Here is another example. You've got face images or you've got handwritten digits. Now, if you can see that if I was to consider this image, let's say 7, as is, if I was to consider, let's say, a raw image, it would have many rows and many columns, and these rows and columns would have 1 and 0 information. So I couldn't just use them as is. What I do is I extract these features, and based on those features, then I classify these handwritten digits into individual or separate characters. Now, this feature extraction would again lead me to form a lower dimensional dataset from a higher dimensional dataset. Okay? So the original dimension of this handwritten digit is much bigger, and the one that we have formed later would be much smaller. There are two key methods of dimensionality reduction: feature selection and feature extraction. We'll be looking at both of these in detail. A feature selection, by definition, is choosing k dimensions which are lesser than the original d dimensions, ignoring the remaining d minus k dimensions. Okay? So feature selection involves selecting some features and discarding some features based on their importance. Whereas in feature extraction, we project the original d dimensions onto new k dimensions and then use these k dimensions or a subset of these k dimensions. Okay. In feature selection, if we consider that these are the original dimensions, or this is the original data we had, we see the impact of each of this data and then we select some of this. Okay? So there are total n combinations by which we can choose any of the useful features that we need. In feature extraction, we find the effect of these data and we see which one is useful, and then we modify these. Okay? So the original x dimensions or x data are changed into y, where the dimension of y is smaller than the dimension of x. So given a set of points x1 to xn, where each of these belongs to the real dimension, we convert the x's into y's, or this dimension into this one, while keeping both of them in the real dimension, and the total number of dimensions of xi is much lesser than yi, or we find a solution in a lower dimension.